for like 1-2 seconds. That's it.
Okay.
Good day, everybody here. Thanks, Professor Krishna Reddy Garu, for the kind introduction. I wanted to know whether the screen is visible to everybody.
Yes, sir. The screen is visible and you are audible too. Very good.
Thank you very much, sir. Thank you very much. I am really delighted to talk about some of our research work in front of audience from 30 different countries. I hope most of the countries have coastal or ocean front in their countries. So this topic will be certainly useful for all those countries. This is the topic, some recent innovations in coastal structures. The main aim of this presentation is to show you some of our recent research outcomes, mainly on wave damping structures or wave energy dissipating structures. Because you know, from the open ocean, the wind generates waves and wave propagates from deep water. Finally, it dissipates the energy in the coastal area. When it is dissipating the energy, naturally it has to do work to dissipate. So it dissipates by eroding the beach. And as beach users, we wanted to save our beach from erosion. Around the world, many different solutions are used, and they have its own merit and demerit. Working in the Gulf countries, we don't have enough good quality stones. So we need to go for alternative wave damping structures. So last 10 years, we were working especially on this topic, and we have come up with some good solution. This is what I'm going to share. Out of this, the first solution is floating breakwater. Second one is slotted vertical barrier. Then scrap tire also is used as wave barrier. The flow of the presentation will be like this. First, I will tell you the conventional way of wave damping people use around the world. Then a few minutes, why innovation is required on wave damping structures. Then direction of the innovation. When we do innovation, what is that we should have in our mind for the innovation? Then different structures, and conclude at the end. The whole world has about 1 million kilometers of coastal length. Really a huge number, 1 million kilometers, the whole world. Out of this 1 million kilometers, nearly 30% of the beaches are eroding. That is a problem. Rich countries, they can go for any type of solution as they wish. Poor countries, they cannot go for such solutions. So our innovation helps developing countries, also developed countries, from economic point of view, from sustainability point of view, environmental point of view, construction point of view, all those aspects. So we thought of for the innovative solution. For people who are new for coastal engineering, I wanted to spend 1 minute. When a beach is eroding, people go for different conventional solutions. These are all the conventional solutions. If this is your property here, top left, you have a property, you want to protect your property, and you don't need beach, then people go for sea walls like that. The top right is another way of protecting beach from erosion by dumping stones parallel to the beach like this. This is called offshore breakwater. Third one is structure perpendicular to the beach. It's called a groin. These three are main conventional solution people use around the world. They need to be selected based on our requirement, marine environment, wave condition, all those points we have to keep in mind before selecting these solutions. For example, groin and offshore breakwater, people go mainly if they need beach. The sea wall, people go only for protecting their property. They don't want beach. People also go for caisson type of structures like Japanese people, or in Italy, people go for caissons like that, especially in deep water. When water depth become more than 7, 8, 9 meters, construction of rubble mound will be very, very expensive. In mild and moderate wave climate, like a Gulf, where waves are mild, people go for even floating type of structure like this, floating breakwater, properly moved and anchored to the seabed. The problem, main problem with conventional structures, they are expensive, first of all. Number two, environmentally, it have a lot of issues, side effects, several side effects. For example, if somebody build groin, on the upstream side, you will see beach, downstream side, you will see erosion. So that means, see, we are not solving the problem of erosion. We are just shifting the problem. So morphological changes are always a big issue. And then dumping stones in many coastal area means we have to dump on natural corals. So they destroy the corals. So coral rich area, people don't go for stone based breakwater. Even if stone is available plenty, they don't go for it from environmental point of view. And nowadays, many countries, they don't like rubble based solution like Netherlands. Netherlands nowadays, if an area is eroding, they go for artificial nourishment using sand. Though it is expensive, you have to dump stone every year, still they prefer that. Because it is not elegant. Dumping stone, tourists, particularly mainly tourist people, they don't like. Visit site where a lot of stones are dumped on the beach, either on the beach, parallel to the beach, perpendicular to the beach. So if a country income is mainly from tourism, and it is better to avoid this type of solution. And many places, the foundations are not strong enough to hold the load of the rock mountains, like Kakinada in India. The seabed is silty and the strength is very less. The dumping stone means a stone will keep on sinking. So many countries around the world, they have similar foundation. So stone-based solution will not work. Another important problem for civil engineers is very long construction time. The reason is, imagine you are building a barrier at 5-meter water depth. The bottom width of the structure will be 5 to 6 times the water depth. So it will be around 25 meter bottom width. So imagine the order of volume of the stone required. So handling such stones using pontoons, lifting, placing one by one means it takes many, many months. So construction, very large construction time. Rubble mound barriers are not suitable in many places like deep water. It is not suitable from cost point of view. Another most important reason is non-availability of good quality natural rocks in many countries. Typical example is Gulf country, Kuwait, and all the Gulf countries here. They don't have good quality rock for this type of application. We have to import them from abroad. By the time the rock reach Kuwait, 1 cubic meter of rock costs almost closer to 80 to 100 US$. So it becomes very expensive to import rock from abroad. This is the reason we have to think for innovation. So we have to think alternative for stones. We have to think how to reduce the volume of material, hence overall cost. We also need to think how to reduce construction time. Normally, marine environment construction time is always very high because of the risk, because of high wave climate, sometimes storms, sometimes cyclone crossings, climate change effect. So construction time is always larger in sea-based construction. And the environmental impact we need to reduce. So alternative is required. We also make structure which looks beautiful, aesthetic point of view. And many structures, we need to increase the functional value of the structure. For example, wave damping means wave energy dissipation. Is it possible to increase the wave energy dissipation compared to conventional structure? This is what we think always. So with this background, I'm going to give some of our solutions. Solution number 1 is an innovative floating breakwater. We got a US patent for this during 2016. This is a patent. The idea came to us from this particular figure. This figure is a structure floating, and the structure bottom has a wall, skirt wall. From the bottom of the skirt wall down to the seabed, some meters of space is available. The ocean wave, its property is the energy of the wave is high closer to the water level, still water level. The energy of the wave is high. As you go down towards the seabed, the energy reduces cost hyperbolically. So basically, if we tackle the energy closer to the free surface, either destroy the energy or extract the energy, like a wave energy device, extract the energy, or reflect the energy back to the sea. If we do any one of these things effectively, then the energy on the lee side is either a port or harbor or a swimming, open sea swimming, or a beach, or a construction activity or aquacultural farm, whatever it is, the backside is the area where engineering activities are going on. So if you have a structure like that, then you can reduce the energy on the lee side. So then we know this particular basic property. This type of a floating structure around the world, people have invented many different floating breakwaters. If you Google it, you will come across many different floating type breakwaters. But then we have to see this application. Normally closer to equator, from equator say 20° north and south, most of the countries, their island have good coral belt, corals like this. So if people wanted to use such island, they need a small marina. So this type of marina, we cannot dump stone because of coral. So to build a marina, we can use floating breakwater. Also, the very large crude carrier, they carry large crude, for example, from Gulf country to different countries, say India. They normally move it in deeper water of 20-25 meter depth. But then, if you take a typically Arabian Sea, for example, it is calm. Arabian Sea is calm during November, December, January, February. So during such a time, there is no problem for loading or unloading of crude oil. During monsoon, June, July, August, there are very severe waves. So during such a period, the floating body, the response, dynamic response, will not allow safe loading or unloading. In such situation, we need to provide a damper, wave damper, like the one I have shown in this figure. A fixed wave damper will be very, very expensive. So we have to go for a suitable design of floating breakwaters. Similarly, the coastal protection of island or mainland, it is appropriate to use floating breakwater, provided the waves are moderate. This type of floating structure designing is very challenging in high wave energy climate. It is challenging. Normally, it is useful for moderate wave energy to low wave energy climate. Also, you know, nowadays, thousands of fish cages are there in the open sea for aquaculture. Many countries, they wanted to do it to produce enough fish for the country. So these type of aquacultural cages, also we need to protect from severe wave action to reduce the load and hence to optimize the design, reduce the mooring load and hence cost saving. Now, from that idea, the fundamental principle of a floating breakwater, the top figure shows if you have 1 meter wave hitting the structure, you wanted to reduce it to half meter on the other side, that is a 50% damping. You need at least 18 to 20 meter wide structure with a 2 to 3 meter draft. This is the basic literature says. Our idea is to cut the structure into two parts, save first 50% material. From the 50% saving, use 10% material to build skirt walls and introduce like a trapping mechanism under the structure. So now, when a wave is acting on this type of structure, which consumes only 60% of the material, will it perform the way the mother structure is doing, or will it perform better or poor? We don't know at the beginning. So this is a question at our mind many years back. We also thought, instead of single compartment, if we introduce one more wall, 2 compartment, or introduce another 2 more wall, 4 compartment, will they help improve the wave damping? This was the question at our mind. So the answer is we have to go and do scientific investigation using experiment in the laboratory. In case the option number 2 on the right hand side here, its effect is same as option number 1, then of course people prefer option number 2 because it saves 30 to 40% of the material. What we did a model, physical model testing in our laboratory. The physical model, we made it using Perspex sheet. The bottom plate, as we were discussing, 2, 3, and 5, we also introduced porosity at the bottom of the plate. Because you know, when fluid is entering through such a porous medium, the dissipation augments. That is the basic theory of fluid flow in a porous medium. So we introduced also porosity, different porosity. We varied the porosity and we did the test in the laboratory. In the test, we measured the incident wave height, wave coming from the open sea, and we measured what is the wave transmitted. And we also measured the wave reflected back. We selected many configuration, many different configuration, because when we do a study like this, we need to do study on many configuration and identify the optimal one. That is the objective. What is mean by configuration here is the porosity in the wall, number of walls, and the wall penetration. So all these things are varied. We were doing the experiment for 29 different configuration. Configuration 1 is a reference, a pontoon without any addition of skirt wall is a reference. With respect to this reference, how other configurations are performing. This is our motivation. I tell you the final result of this study. If you see this picture, x-axis is floating breakwater configuration. The number here from 0 to 30 indicates, or 1 to 30 indicates this number. This number. For example, the last few are a pontoon with 5 different skirt wall, porosity 0, 5, 10, 20%, for example. Similarly here, the last 4 are 3 skirt wall, 0, 5, 10, 20% porosity. Same height of the skirt wall. So like that. So you can see here, these 4 are 5 skirt wall, 3 skirt wall, 2 skirt wall, single skirt wall of different depth. To tell you clearly, this is 5 skirt wall, 0% porosity, 5%, 10%, 20%. Basically, what we have given here is if some user wanted to have a floating breakwater which is 50% effective, 50% effective, this is what the number, 50% 0.5 means 1 meter wave height is acting, on the other side the wave height is 0.5 meter. If it is so, these are all available. The meaning of this, number one is without skirt wall. You need a pontoon of 17 meter wide, 17 meter wide to give this performance. Whereas if you have a 5 skirt wall, you need only about 8 meter wide with the 5 skirt walls. So both of them are same. So what it means you save a lot of material without altering the performances. So that is what the meaning from experimental investigation. That was a technical thing. Then we wanted to work out the economics. We did the economic assessment. What we did for economic assessment, I will tell you, we considered a marina, a 200 meter wide marina. This is the open sea here. One solution here is rubble mount breakwater. This blue color, straight, this one is rubble mount breakwater. Another solution is floating breakwater with skirt wall. So both the things will work. So in a marina, the boat can come from open sea, they can go in, they can stay here, then they leave. So two alternatives of this particular structure we consider for economics. So a typical rubble mount breakwater looks like this. The outer side of the rubble mount breakwater, 1:2 slope, that is basically required for stability. Inner side is 1:1.5. You will have inside here is smaller stone, very small stone to smaller stone. The final outside is armor stone. Option 2 is floating breakwater with the 5 skirt wall. What we assumed from construction point of view, a floating breakwater of 12 meter long and almost this width, we considered such a floating breakwater. These are all empty space required for flotation, buoyancy. And the wall thickness is 0.3 meter. And bottom you have 2 meter skirt walls of 0.2 meter thick. And it is moved down like that. So this is floating breakwater option. We worked out like any engineering volume cost assessment, we worked out first of all the material volume, then we use the unit cost in Kuwait. So if anybody is using an economics, they will use the unit cost in their respective country. So this particular assessment we have done for Kuwait. At the end, you know, the cost required for 200 meter construction of rubble mount breakwater is 1.38 million Kuwaiti dinar. One Kuwaiti dinar is $3.3. So that means almost like more than 4 million US dollar. Whereas for the same application, if it is floating breakwater, we need only 0.58 million KD. That is almost like much less than 2 million dinar. So cost of the floating breakwater to cost of conventional breakwater is about 0.42. This is what we got for Kuwait as an alternative from cost point of view. Then we have to see about the environmental aspects, merits and demerits. The major merit of rubble mound is it is a natural material, so maintenance will be very less than 1% of the construction cost, and life will be very long. That is a major merit. Major demerit of rubble mound is, see, it will not allow any water from the open sea into the marina. So water quality inside the marina will be poor if we go for rubble mound. And if seabed is coral or seabed is not strong, then you need a higher cost of investment for this. On the other hand, floating breakwater, better water quality inside the marina. Seabed strength is not an issue at all. Coral on the bed, no problem. It is mobile, moving, so you can slightly reorient it when wave directions are changing. That is a big advantage here. Demerit is the maintenance will be expensive. About 5% of the initial cost we have to spend to replace the mooring line or some of the structural component. And there will be some waves on the rear side. So this is a merit and demerit. So we have to look into the merit and demerit, science as well as economics for selecting a suitable solution. Now I'll go for solution number 2 in our study. It is an innovative way of wave energy dissipation applicable for 2 solutions. One is erosion protection. Another one is construction of new port or harbor or marina. This study also we did from a project. For 3.5 years, we did the study, and we got a US patent during 2016. The idea started from a problem in the field. If you visit a marina anywhere in any country, if you visit, inner side of the marina, you will see rubble mound, a sloped rubble mound. Why people build this rubble mound? The boat moving inside the marina create waves, and we have to destroy the energy of the wave. Otherwise, wave will come, hit the vertical wall, reflect back, and you will have always wave inside. It is not advisable to have waves inside for operation. But unfortunately, this structure, you see how much space it occupies. For example, if the water depth here is about 7 meters, this will occupy almost like a 15-16 meter wide. So we thought, is it possible to reduce the width from 16-17 meter to just a few meters using a elegant structure? That was the idea. And the idea, since as I was telling you, in Gulf countries, stones are expensive, as I told you. So we wanted to replace the stones by high strength polymer material, which is a byproduct of crude oil refining. It is available locally. So that way local materials can be used. And the material consumption, lesser, better. So these are all the ideas in our mind. More elegant, and from science point of view, is it possible to have a wave damping system which is better than rubble mount. That is what we were thinking. So then we did the study in our laboratory. Finally, we came to a structure of this nature. What you see on the right-hand side here is a conventional way of building the inner side of the harbor, conventional, using rubble mount. And this is what the new type of wave energy dissipator. What it contains, few rows of walls, porous walls like that. On the top of the wall, you can build berthing space or space for keeping material, which is not possible here. Berthing space here. The merit of this compared to this, the width occupied is much less. See, this may occupy, as I told you, anywhere from 10 to 20 meters, depends on the water depth. This will occupy only 1/3 of this width. And I'll tell you the volume of material required for this construction, sometime even less than 10% of the volume of this material. And here the materials are stones and concrete, whereas here it is high strength polymer. So then other advantage, this whole system can be prefabricated and assembled quickly in the field. We are not occupying a lot of foundation space either. So like that, there are many advantages. There is no corrosion if you use a high strength polymer. A typical view of the marina look like this, very elegant compared to a marina with the rocks. So it will attract people to visit. Tourists love to visit such type of marina. What we need to give to the world is optimum number of wall, optimum porosity. This is what we need to give from science. If anybody approaches us based on the field condition, we will give them this many number of wall, this order of porosity will work. So that is what we do. What we did is, we did the study first for a benchmark. The benchmark, I will show you, the benchmark is typical rubble mount structure. This is a benchmark, or the structure people use in the world. So this benchmark study with the rubble and a different type of armor, we did the study first for this. Then we moved to the investigation with slotted walls. For example, in a typical wave flume, if we do the study in a typical wave flume, when the waves are acting on the structure, you will see this is the way it responds. So we selected 7 different conventional configuration, and we selected many different configuration of slotted barrier like this. You can see when waves are acting, it dissipates the energy when it is passing through the structure. So when it dissipates the energy, the reflection will reduce. That is the principle. So in the waveform, this is how the one of the view looks like. We have selected 30 different configuration, starting from one wall all the way to 6 porous wall. We also varied porosity from 10 to 50%. So 30 different configuration and a few conventional configuration like that. See here, the first 7 is conventional. Rubble mound with different armor from 8 all the way to 37. They are all slotted walls, different number, different porosity. So we measure the wave reflection. From wave reflection, we know what is the wave energy dissipation from law of conservation of energy. I wanted to emphasize here, this percentage here indicates volume of material required for different walls and different porosity. For example, for a particular location, the solution is 6 walls, 50% porosity is a solution. The volume of material required is only closer to 12% of volume of rubble mound. So this is basically this gives an indication of economics. I am trying to explain the principle, how we select the better solution is like that. On the y-axis here is reflection coefficient. Reflection coefficient 1 means when a wave is acting on a wall, it reflects completely back, 100%. Reflection 0, coefficient 0 means when a wave is acting, the structure is dissipating all the energy. So what you see here, from 1 to 7 is conventional. This is the behavior of conventional structure. From here to here is the behavior of the different configuration. 1 wall to 6 wall, 1 wall to 50%. What we have done from the conventional structure, the best one is this. The best one is efficient with 0.6. So we draw a horizontal line and the behavior of this is provided here. The new structure, which is less than this line, all these configuration, they are much better than conventional structure. That is what the meaning of this particular plot, to tell you in a simple way. So for a owner who is going to build a marina, he will look at this figure and he may select this, for example, this point, because the lowest reflection is better. So this point number 36, if we select, 36 is slotted wall, 5 wall with 50% porosity. So if you provide that, it is 2 times better than conventional rubble mound breakwater. That is what the advantage of this structure. Okay, the volume it is going to consume is only about 10 to 11%, but the effect is 2 times better in dissipating. So this is the real bonus for selecting this type of structure, either for new port or harbor, or for seawall, even for seawall construction. We have given the available possibilities in a tabular form, in a clean tabular form for different sea conditions. This is what finally fetched us the patent. We came to know at the end of the study, this type of structure is better than rubble mound slope structure, almost like more than 2 times better. As I was telling you, it can be used for marina, new marina. Somebody build new marina, it can be used, or new port and harbor, it can be used like that. How the structure appear for a big port compared to rubble mound breakwater? In a very huge port, the rubble mound breakwater in deeper part will be about 10 meters deep. So in such location, if we use this technology, on the seaside, you will have few porous wall. On the lee side, rear side, this is the harbor side, you will have few porous wall. On the seaside, when waves are acting on these structures, they will dissipate energy and some wave forces will come on the structure. On the harbor side, the waves generated by boats and ships, they will be dissipated to some extent by this structure. This is how it look like in a cross section. In a plan view, again, as I was telling for the previous case, we can go for prefabrication technique. The width of each unit can be designed based on carrying capacity of the facility, and it can be done easily like that. So this we thought, even new way of construction is possible. Similar to the previous case, we did the economic analysis. Exactly the same way. For the marina, one is rubble, another one is the new wave energy dissipator. We already know what we did for the option 1. This we have seen already. For the option 2, again, we worked out all the unit cost, construction, every details we worked out, starting from materials, unit cost, then we came to the final cost. The rubble mound breakwater cost about 1.4 million KD, whereas the new wave energy dissipator cost about 0.8 million KD. The ratio is 0.6. That means nearly 40% cost saving is possible with many environmental merits. The merit of the new wave energy dissipator is less volume of material, quick construction, more environment friendly, more water plan area inside the marina, all these things. Demerit, maybe the maintenance cost will be a little bit more. Now I will go to the third one, wave damping in the coastal area. This is our last structure. We got the US patent during 2020. It is similar to the previous one, but then you allow wave to act on the structure. Progressively, wave energy dissipates. After certain dissipation, the wave energy emits here, transmits here. We want to know what is the transmission by going for different number of walls and different porosity. That was the idea. So we did the study first with the conventional structure of rubble mound breakwater. We did the study first with this. Then we did the study with the slotted wall in the wave flume, in our wave flume. We got the results of merit and demerit. What we can provide, for example, see, these type of things is replacement for offshore rubble mound breakwater. Instead of rubble, we can use slotted wall. We have in our mind two different clients. One client initial budget is not a major issue. So that type of client we have optimal solution. For client who have initial budget is an issue. For such client, also we can select optimal solution. We provide optimal configuration, meaning is number of walls, optimum porosity, which performs better than rubble mount breakwater. This is what the meaning of optimal configuration. It should perform better than rubble mount. Number two, for designing such type of structure, we need the design wave forces, moments, and wave impact pressure. All these elements we measured in the physical model. So we can provide these informations for optimal design of this structure. We took a case study for Kuwait. In Kuwait, the wave climates are moderate. So for a wave of 0.9 meter, if we select two walls with the base concrete base of 0.5 meter thick, 4 meter wide, required for stability, and 10% porosity. If it is built like this, 0.9 meter will become 0.27 meter. 0.27 meter wave will not erode most of the beaches around the world. So that is what the importance. So particularly when people have a lot of erosion, 0.9 meter wave will erode most of the sandy beach. So if people build a wave barrier with the two walls, 10% porosity, it will solve the problem of beach erosion with much less cost. The advantage of this, it will reduce the wave energy transmission, but the mass of water will move forward and backward. So quality of water is maintained here, unlike rubble mount breakwater. So water quality is maintained. That is a major advantage from environmental point of view. Last but not least is a cheapest solution for wave damping, the scrap tire wave barrier. This study is an outcome of a PhD thesis of one of my friend from Kuwait University as a faculty, Dr. Ahmad Al Yusuf. He did his PhD in US, Florida. So for his PhD, this topic was selected and we did the physical model study in our laboratory. The main point here, country like Kuwait, we have much more than 1 billion scrap tire every year. No, around the world every year. Many places around the world you will see scrap tires like this. People use scrap tire for different applications in civil engineering. And then we thought, is it possible to use scrap tires in an appropriate design method to reduce wave energy transmission? So in the thesis work, we selected 9 different configurations of the scrap tire. These are scrap tire. The scrap tire density is just closer to 1. So it will float easily. Little bit more than 1, so it will go down in fresh water. So we have to provide buoys for floating. So this is option 1, 2, option 2. So waves are going from here. It will interact with the scrap tire. Scrap tire will respond dynamically, dissipate some energy, and wave will move. So these 9 different combinations we adopted for the study. And this is how it looks like in the laboratory. So waves come from one side. After interacting, you will see a lot of turbulence around the structure. That is the indication of dissipation. Then wave transmits. A typical plot from this study is this. The y-axis in this plot is coefficient of transmission. This meaning is 0.4 means if you have 1 meter wave acting, 0.6 meter wave is damped, 0.4 meter wave transmits. That's the meaning. So we have this type of plot for different wave condition from this study. It is available. This is what required for selection and design. Again, we took the study results to design a typical floating breakwater for Kuwait. An arrangement like this, with 11 meter wide and mooring. This will give wave damping, proper wave damping, useful for wave erosion protection. There are a lot of questions about the leaching of scrap tire. Many literatures, many people around the world, they worked on leaching property. And they said the leaching property is very minor from scrap tire. So we can use good quality scrap tire, very cost effective for wave damping application. So with this, we conclude we have done some innovative work to come up with few different marine structures, mainly for wave damping, because wave damping is required for many applications. One of the urgently needed application is coastal erosion protection. So from our study, we focused on how to reduce cost, how to look at better environment, how to improve the aesthetic value, reduce the construction time, improve the function, engineering function. So all these things we have kept in our mind while doing this study. I hope these results, if people use it, is sustainable. Thank you very much for your patience.